morning. How's everyone doing? Good morning, everyone. Hope everyone has a relaxing weekend. Welcome back. Happy Monday. So we are going to finish our chapter for today. The last topic that was left is rule, and we will cover that topic today. We uploaded some practice problems for chapter 4, and also a formula sheet is uploaded there that has most of the important formulas for chapter 4 there. So take a look at that. Mm, I will talk about Bayes' rule today, and we'll finish the chapter. But at the same time, practice problems are uploaded on Canvas, and there are not very many problems. I'll specify which one you need to work on, and then the solutions for those problems will be uploaded on Canvas by Wednesday. And on Wednesday, we will have review session for chapter 3. On Friday, we will have for chapter 4. And next Monday, you will have your test 2, which is on chapter 3 and chapter 4. Also, you must email or let's say an announcement from me regarding starfish reports and flags. So as mentioned in my announcement, if you receive that flag, that doesn't mean that you are failing the class. Again, we need to submit that starfish report twice a semester, and one is after 7 weeks and one is after 11th week or 12th week. So that starfish we have to mention, or we need to submit what is your current grade, how many assignments you're missing, what is your class average, or if you're a lot of assignments, your class average is below 70%, then make sure you talk to your advisor and take a decision. If you want to continue in this class, then definitely you need to work hard. So far, our only homework quizzes and test 1, but we have test 2, final exam, which is 30% off your actual grade, and project. We still have a lot to work on, so make sure that you want to stay in the class and you are on the border of failing and passing, then make sure you work hard. And if you need any help or you need any resources, we working at Math Help Center at her class. She is helping us during our office hours also. And Mr. Philip is also one of our tutor at Math Help Center. So make sure you work hard with either the Math Help Center tutors or work with me or make study group with your classmates. So whatever helps you to get through that. And if you think that you need help from my side understanding anything, feel free to join my office hours or send me an email or Miss Minion, whatever works for you. Let us know. All right. So last Friday we were talking about conditionality. So in chapter 4, we talk about the probability, rules for the probability, what kind of event are working with. See, something looks like probability. that means looking for the probability of an event or probability of the second event when we know that there is already one event happened. So if those two events are independent, the probability, the conditional probability events are independent. You guys can hear me, right? Just want to make sure. Can you guys hear me? Anyone? Can you guys hear me?
Yes,
I can hear me.
That
I'm not sure if
like the connection kind of like sounds static.
Yeah, we can hear you. It's choppy sometimes on my end, though.
Can you guys hear anyone? Okay. Can you hear me? Okay, so looks like you guys can hear me, but worst case, if you can't hear me, send me or let Miss Minia know, and she can send me a message, and I can go over with that concept again. So last time we were talking about conditional probability. What is conditional probability? So you are looking for the probability of an event under a specific condition, and that condition can change the probability of your other event that is happening. So when we are saying probability of A under the condition B, we use the symbol this one, A given B, and this symbol is the probability of A under the condition that B is already happening. So probability of an event A given that B has the experiment was performed. And when we say probability of A given B, the formula that we use is the intersection of two events divided with the given probability. Rule. Bayes rule is an important application of conditional probability. I'm still wondering if you guys can hear me or not. Minion, can you hear me? Minion?
I can hear you, but I'm
Can
not
one
sure
of
if
you
you
tell
can hear
me if you
me.
can hear me?
Monica, can you hear me?
Okay. Why it's Can one of you unmute and let me know if you can hear me? I can hear you. Can you guys hear me? Looks like some of you are dropping and joining again, so I don't know what's going on, so that the connection is really bad. I don't know what to do because yes, I can hear you, but can you hear me? Now I cannot hear you. Let me try at a different place.
Monica, can you hear me?
Can you hear me clearly now?
We can't hear you. I don't know if you can hear
a few
us.
minutes
Not
ago,
today.
but sometimes I can't. Now I
Okay.
can't.
We can't hear you.
I think it's going to.
There's a lag between when you say something and when you can hear us.
Tell me now if you can hear me. Yeah. You can. Okay, perfect. So hopefully like it will stay. It's clear now? Okay. Now, worst case, if the part is not clear, we can go over. So, Minin, now you can hear me? Can you hear me? Oh, God. I'm not sure.
It just keeps cutting in and out. Like I can hear you for a second and then it will stop and then I'll miss like everything you're saying in between.
Okay, so let me just sign out and sign in again, and hopefully that will work, but let's see. You guys just stay there and let me sign out. an event, which is B, under the condition that this has already happened, we denote it like this. And this is called the conditional probability of B under the condition that A has already happened. Or say that probability of B given A. This is what we did in the last class, probability of B given that A has already performed or already done. And the formula that we use is the intersection of these two events. Either we can write B intersection A or A intersection B given with the probability of, divided with the probability that the event that was given to us. So probability of B intersection A under the condition that A has already happened, and this should be definitely greater than 0 because that event has already happened. We also discussed that if B intersection A, instead of B intersection A, if I write A intersection B, it's not going to change anything because when we are saying intersection, we are talking about the common part between A and B. We can write this as A intersection B or B intersection A. So if you write A intersection B or B intersection A, it's not going to change anything. But if we flip this, then these are two different things. When we are saying probability of B given A, that means A has already happened. When we are saying A given B, that means B has already happened. So then the formula, the numerator remains the same, but the denominator will change depending upon what is given to us. Questions about conditional probability? Anyone has any questions about conditional probability? And just want to make sure that you can hear me. You can hear me, right?
Yeah, we can hear you.
Yes.
Okay, just want to check that. So this is about the conditional probability, and we have done one example in the last class. Let's say I know the probability of A intersection B, let's say just some number, and I know the probability of B is 0.7, any number that I have. So what is the probability of A given B? So if I'm looking for the probability of A given B, I know the intersection and I know the probability of that event. I can divide and I can find this. And this conditional probability also have a multiplication rule. And what that multiplication rule tells us that if we know the probability of the given event and we know the individual probability, how can we find their intersection? Their intersection is the product of these two. So if I'm looking for the probability of A intersection B, and I know the given probability, I know the individual probability, then it's the individual probability times the given probability. So this is called your multiplication rule for conditional probability. So if we need to work on the conditional probability, if these numbers are given to us straightforward, it's easy to plug. But what happens if they are not given to us straightforward? If they are given to us in the word form and we need to find the individual probabilities or the given probability, how do we do that? So here is an example. So let's look at this example. Roll 2 fair-sided dice. What is the probability that a sum of 3, given that a sum of 3 or 5 has occurred? So read the question first, what information we have in this question, and what are we going to do here? So it says that roll 2 fair 4-sided die. And again, when we are saying 4-sided die, the max outcome we can have only 4. 1, 2, 3, 4. We have done an example on roll 2 fair 6-sided dice where we were looking for 36 outcomes and we worked with that. Now let's say we have a die and that has only 4 outcomes, 1, 2, 3, 4. And they are fair dice. That means when you toss, each outcome has equal chance of coming. So if I roll a die, I get either a 1, 2, 3, 4. Let's say I take 2 dice. So one same thing we can take as red and green color, like how we did in that example. So it says that two fair die, four-sided die, what is the probability that a sum of three or five, given that a sum of 3 or 5 has occurred? So first of all, we need to know how many possible outcomes are there. And then we can assign the probabilities for what information we have. So how many outcomes are there? Any guesses? So when we roll two six-sided dice, we got 6 times 6, 36 outcome. Now we are rolling two four-sided die. What do you think? How many possible outcomes we can have? Guesses? Calculation?
16.
16. Perfect. So same thing. We keep one fixed, and the max we can have. How many? 4. And same thing. You can do it. And very similar way, like how we did the previous one. So 4 rows and 4 columns. So you have 16 outcomes. So first of all, we know how many outcomes are possible. So each outcome has 1 out of 16 chance. Now, what is the probability that the sum of 3? So let's say the sum of 3 we take as probability of A is the sum of 3. Let's say we take an event A as sum of 3. So under what condition we can get sum of 3? Or how many outcomes have a sum of 3? This and this. These are the only two outcomes. So 1 out of 2, 1, 2, and 2, 1. So these are the outcomes for A. And the probability of this is 1 out of 16, and this is also 1 out of 16. So the probability of A, which is sum of 3, is 2 out of 16. Questions?
And when we're doing probability, do we simplify the fraction?
You can simplify the fraction if you want. Yeah. So when you get the answer in the end, it depends. Like you can leave it in the fraction or you can write in decimals.
Thank you.
You're welcome. Because you know that the probability is between 0 and 1. So you can leave it as a fraction or decimal. So this is one part, probability of 3. Now, what is say sum of 3 or 5? So when we are saying sum of 3 or 5, so let's say B is the even sum of 3 or 5. So that means we are talking about either the outcome is 3 or the outcome is 5. So let's make a sample space for that event. So 3, we already know for 3 we have 1, 2, 2, 1. For 5, how many outcomes will be there? Let me
2.
2, okay. So let me just fill this gap so that we can see. 2, 2. So let's see, where can we get 5? I can get a 5 here. 1, 4. I can get a 5 here. 2, 3. I can get a 5 here also. 3, 2. And I can get a 5 here also. And I understand why you said 2, because 4, 1 and 1, 4. But again, we are taking individual outcomes. So the probability, when we look at the B, the event B has how many? 6 outcomes. And each has probability 1 out of 16, right? So that means we know the probability is 6 out of 16. Everybody good with that part? So now you are looking for what is the probability that the sum of 3. So that means 3, the sum of 3 we have taken as A. Given that the sum of 3 or 5, given that B, and we are looking for this part. So we know that the sum of 3 is 2 out of 16, and we know that the probability of B is 6 out of 16. But now what our question is asking is, what is the probability that a sum of 3, so sum of 3 we have taken as A, given that a sum of 3 or 5 has occurred. So we know this part is given. So plug your conditional probability formula and see what information you have. So this will be their intersection divided with probability of B. And what is the probability of A and B? So what is their intersection? So intersection means what is the common between A and B. So look at your A and B outcomes. What outcomes we have common? This outcome, I have this here. And this outcome, I have this. So their intersection is basically they have two outcomes common, and the probability of each outcome is 1 out of 16, right? So their intersection is 2 out of 16. And what is the probability of B? We already calculated the probability of B is 6 out of 16. And then when you solve it, this will be. And then if you want, you can divide it and write it in decimal. So when you are talking about conditional probability, it's not always that the values are given to you. Sometimes you can get the word problem, and from there you have to find the probability of each outcome separately, depending upon what information is given to you. So this is about conditional probability. When we are talking about Bayes rule is an important application of conditional probability, where we are trying to find the probability of one event with the given event as a combine. And let's just read this Bayes rule. So this one is about the conditional probability. We did this tree diagram last time. So we said that tree diagram is a better way to represent individual probabilities when you are consisting of sequence of outcomes. And each outcome can be represented as individual probability. Like here we toss 2 coins. Let's do this example so that it will make more sense. So this is again an example of conditional probability. It says that an American Life project finds that 93% of the teenagers use the internet, and 55% of online teens have posted a profile on a social networking site. What percent of teens are online? And so read the words. In the previous example that we did, we said that 3 or 5. Now we are saying online and posted. So basically we are talking about intersection. So we are looking for probability of online intersection posted a profile. So that's what you are looking for. So when you are looking for and, you know that you are looking for conditional probability. Conditional probability, this is the multiplication rule. So you are looking for individual event times the conditional probability of that event, right? So let's look at this one. So when you make a tree diagram, start from here. First, just look at this. You have randomly selected teenager, and 93% are online, and remaining is 7%, which is 93 plus 7. If this part is not given to us, which is not given in the question, but we can calculate because the sum of these two should add up to 1. So if this is 93%, this is the remaining 7%, and you convert it into decimals because we are not using percentages here. And once the teenagers are on internet, then only they can upload a profile. If they are not on internet, they cannot upload a profile. So they uploaded a profile, which is given in the question is 55% of them uploaded a profile. How many of did not upload the profile? The remaining from 1 is 45%. So uploaded a profile, yes, not, yeah, is remaining. Same thing, 7% does not have internet. If they do not have an internet, can they upload a profile? And the answer is no, they cannot upload the profile. So if this is 0, the remaining is 1 because the sum should add up to 1. Now, how do we write these individually? What is this 93% represent? This is how many students or how many teenagers are online. This is the probability of online, 93%. What is this 55%? We cannot get this 55% until we know that they are online or not. So this will come given that they are online. So this is the probability given that the teenagers are online and they posted a profile. So that is your 0.55. Same thing, this is the probability that the teenagers are online, but they did not upload the profile. No profile. Same thing, you can find the probability of not online. And this is the probability of uploading the picture, uploading the profile. Sorry. Profile when they are not online. So these probabilities, or you can say these, this, you will not know until you have something given. So these, when you go to the second branch of the tree, this is your first and this is your second branch. When you go on the second branch, you need to go on the second branch through first branch. So first branch is given to you. So the second branch probability depends on what do I have on my first branch. So that's all. It's you look at the tree and you get that information. So probability of online, 93%. Probability of profile, given that they are online, is 55%, these two. And when you are looking for the intersection, which the question is asking, online and have profile, this is online times the profile and online. You have these two information, you multiply. And once you get into decimals, convert into percentages when you write the answer or write what is the percentage or how many, what percentage of the teenagers are online and have posted a profile. And again, this conditional probability is not like that easy to understand all of a sudden. You need to do a couple of examples to understand what actually I am looking for. Am I looking for the intersection? Am I looking for this part? Am I looking the individual probability? So go back to your book, and there are a couple of examples that are solved on conditional probability. And once you understand the logic of conditional probability, Bayes' rule is only one more step ahead of it. So Bayes' rule is not coming from somewhere else. It is coming from conditional probability. But in Bayes' rule, we are not just looking at the conditional probability of one event. We are looking at the conditional probability of one event under the condition that how many times that event is happening or the total of that event. So let's talk about Bayes' rule. And again, as I said that some examples are uploaded, not example, I said some practice problems are uploaded under your chapter 4 module for Bayes' rule. I will suggest you to practice those yourself first by understanding the concept of Bayes' rule. Once you understand that, then try working on those practice problems. And we will go over those practice problems either in Wednesday's class, or I will upload the solutions for those, or some way we will do that so that you will understand your work, what you did, is it correct or not? If it's not correct, where you messed up. And if we need an extra class to go over that material, I won't mind doing that. And then we can push the exam. But right now the exam is on next Monday, but we'll see how you guys will feel about Bayes' rule in the next class. There will be at least one question on Bayes' rule in your test too, and you will see questions on Bayes' rule in your final exam also. And it's not just about question, it is the application. We use that Bayes' rule in real life a lot. So I hope this Bayes' rule will make sense to you in today's class. But as I said, if not, we will talk about that in the next class also. So what is Bayes' rule? Again, it says that an important application of conditional probability is Bayes' rule. So if we are talking about Bayes' rule, we are talking about conditional probability for sure. It is the foundation of many modern statistical applications beyond the scope of this test. So it says that suppose the sample space is decomposed into k disjoint event, and let me make it here. So let's say this is my sample space and it is decomposed. So that means I have so many events and each event has a name. So this is, let's say, A1, A2, A3, so on, AK. That is mean by decomposed into k disjoint event. So we have k events and they are all disjoint. So they are 1, 2, 3, 4, k. They are not having anything common, and that is the meaning of disjoint events. So we have k disjoint events. So it says that suppose that a sample space is decomposed into k disjoint events. So we divide a sample space into k events, and each event is disjoint, so they have nothing in common. So the intersection between A1 and A2 is 0. The intersection between A2 and A3 is 0. And same thing, intersection between any two events is 0. Now it says that A1, A2, none of which has a probability 0. So all these events, probability of A1, A2, or you can say AK, they all have probability greater than 0. So none of them has 0 probability. So they have some probability between 0 and 1, and they are disjoint even. Such that when you add the probability of all this will add up to 1. Probability of A1, probability of A2. When you add, it equals to your sample space, which is 1. Now it's saying that let C be any other event such that probability of C is not 0. Let's say we have any other event C that is intersecting all of my disjoint events, and that is another event. So it says that let C be any other event such that probability of C is not 0. So I will talk about where is this formula coming from in a minute. So first you understand that we have k disjoint event in a sample space, and there is another event C which is intersecting all of my k events. So first of all, if we need to write the probability of C, what is the probability of C? So probability of C is this whole thing. So this whole thing is a sum of this, then this, then this, and similarly this. So probability of C is the sum of all this. And we don't have all this, but we know that this part is the intersection of A1 and C, and this part is the intersection of A2 and C. This part is the intersection of A3 and C. So we can write probability of C is the sum of intersection of each event with the given probability. So probability of C is probability of A1 intersection C plus probability of A2 intersection C plus probability of AK intersection C. So that is the probability of C. Anyone has any questions up till here? How did we get the probability of C? Everybody good with that part? Yes?
Yes.
Perfect. I just want to make sure that you guys can hear me. That's why I'm asking. So please do not take me otherwise. Let me make it all over again. So once we know the probability of C, now if I'm asking what is the probability of A given C? So if I'm just asking the probability of one event with the whole, or the probability of the second event with the whole, I know that the probability of C is this whole part. So that means if I say probability of A1 given C is the probability of A1 intersection C divided with the probability of C, right? And the probability of C is this whole part. And how do I calculate this probability of C? I know the multiplication rule for intersection events of conditional probability that we just did, which was probability of A given C was their intersection divided with the total probability. But if I'm just want to look for this part, it is the multiplication of these two. A intersection C is. So I can apply this part here when I'm looking for the probability of this or this or this or this. So Bayes' rule, basically Bayes' rule, you are doing the conditional probability. This is the extra part that we are doing. We are looking for the conditional probability of one event over the entire event that is intersecting all of these events. And when we are saying probability of C is the product of A intersection is this, similarly A2 intersection, A3 intersection. So if you look at this part, probability of AI given C, I means 1, 2, 3 up till K events, and take this as the intersection of AI intersection C, and this is the denominator. Or let me just write it here, make it easier. Probability of AI intersection C divided with the probability of C. So this is your probability of C, and this is the intersection. If your I is 1, this will be C given A1 times probability of A1, or you can write this formula as probability of C given AI times the probability of AI divided with the summation of So in the denominator, whatever we have in the numerator, we will have that plus all the other events. And numerator, if I'm looking for A1, I will just look for A1. But here I'm looking for the sum of all. And I know sometimes just looking at the formula does not make sense. So let's do an example, and that example will make sense. And again, there are some examples solved on Bayes' rule in your book. So take a look at that too. So this is an example that is given in your book as well as in your slides. So let's look at this example carefully and hope this example will make sense. The formula, when we look at this, it does not, I'm just talking about myself. When I look at this first time, it does not make sense to me until I apply it in the formula or in the tree diagram. So you can apply this formula directly, or you can use the tree diagram. So this tree diagram is given to us in the question. Instead of giving individual probabilities of all, this tree diagram is given. And let's see what information we have and what the question is asking us. It says that if a woman in her 20s gets screened for breast cancer and receives a positive result, what is the probability that she does not have that breast cancer? So this is given to us that the disease, getting a disease, the probability is 0.00004. You see how less the probability is, 0.00004. So this is the probability of getting the disease. So how much is the remaining? You subtract this part from 1, you get this. So when you add these two, it should be 1. So this part is given. So, and that is cancer, no cancer. So this is the probability of cancer or no probability of no cancer. So I just want to let you know that how do you represent that in terms of probability when you plug it in the formula. So once you know that, now the second part, it says that let's say the subject has the cancer, or not say, let's say the probability of the detecting cancer is this much. So this one is done. Now, when you diagnose it, the test is positive rate is 80% and negative rate is 20%. So this is the probability of test coming out positive, given that there is a disease, right? And this is the probability of test coming out negative, but we know that there is a disease. So we call it false negative. Because again, the tests come out to be negative, but we know that there is a disease. Similarly here, this is the probability of positive test, but there is no disease. So we say probability of positive test, but no disease. So no disease, but tests come out positive. That happens. So when, let's say, we go to a doctor and do some tests, sometimes the tests come out to be positive, but actually, let's say we don't have a disease. And they say that the chances are very rare, which we can say that it's 0.0003, 0.009. And if you go there and you don't have a disease, but comes out to be that the test comes out to be positive, again, we get panic, but we say that none of the tests is 100% true. They have false positive, false negative, and these are the words, or these are the terms. What is false positive or false negative means? False negative means that the test comes out to be negative, but actually there is a disease, and the chances are 20%. And same thing here, the tests come out to be positive, but actually there is no disease, and then it is 1%. And here the tests come out to be negative. Tests come out to be negative, no disease, and negative test. So that's how we represent all these probabilities. Now, the question is asking us, what is the probability that she does not have the disease? So she does not have the disease. So here it says that A1 is cancer, A2 is no cancer, and C is the positive test. So when C is the positive test, first of all, I need to know what is the probability of C. So I will go back to my tree diagram and see where the test is coming out positive. The test is coming out positive here and here. So these are the only two scenarios where the test is coming out positive. So what is the probability of positive test? This time this, and this time this. So that is the probability of positive test, and you add this. So that is your probability of C. Intersection of this time this plus intersection of these two, and you get your test positive. And if you look at on this one, on the bottom, this is your probability of C. Probability of test coming out positive with cancer or with disease is 0.8. And in the slide, there is a typo. In the slide, it says 0.004, but actually it is 0.0004. So just fix that when you work on it. And this is the numerator, and that's the denominator. So try working on that. I guess when you work on these example, it will make more sense. But as I said that, if you have any questions, because first 10 minutes of the class was a mess because of that internet connection. So if something is still not making sense, let us know, and we can go over with that material on Wednesday's class as well. So you will be good to do your homework assignment as well as quiz, and everything will be due, I'm not sure, 17th, I guess. But let us know if you have any questions. And I sent an announcement last night that I will not be available during my office hours today. So, but Miss Minion is available. So if you have any question related to chapter 4 or any concept, you can check with Miss Minion. She'll be available till 12:45. But if you have any questions specific to me, feel free to send me an email and I will reply you back. Otherwise, I'll see you guys on Wednesday. Thank you, everyone.
Thank you.
You're welcome.
Thank you.
Hello.
You'll be good?
Yeah.
Feeling better?
A lot better. Not my roommate though. She's still feeling.
Oh, she's still not well? You said that on Saturday she was fine.
Yeah, she said she was fine on Saturday, and then yesterday she was like, I'm feeling worse again, and then today I think she's still, and then But she measured herself earlier. She said she wasn't having a fever anymore. But so we don't really know what that is. Maybe it's just because of the fatigue. I don't
Yeah,
know.
and I think maybe she did not eat after the vaccine properly, so maybe that might be the reason.